So this again is what's on the long sheet of paper, which I gave out yesterday, which I think you don't have.
Oh, no, I have that. I was serious.
Were you here?
Yeah.
Okay.
Just the-
Oh, is there anybody here who wasn't here yesterday?
Oh, yeah, this one.
Yeah. Okay, well, but again, we're going through this on the long sheet of paper. So the R is the position, the tip of it is tracing out the space curve here that goes, say, like this in my picture. And so we're focusing our attention on where we are on the curve at some particular point in time. And that point is identified by the tip of the R of t vector, which is the one in this color. And there, the black dot, maybe you can see it, is the point on the curve, say, where we're focusing our attention. And so the plane where you would find these vectors, the velocity vector in purple and the unit tangent vector that points like the velocity in blue, and then these at right angles to the first two, the unit normal vector in orange, the curvature vector in brown, the derivative of the unit tangent vector in the pinkish color, and the normal component of acceleration in this color, green. All of those vectors are in this plane that Gauss, who invented this, what we're doing is actually has a name. This is called metric differential geometry. The metric refers to the idea that you can compute the length of the vector, the dot product with itself, take the square root. That's your metric. So you have a sense then of distance between one point and another. And the differential refers to the derivatives. And the geometry, I think, is pretty obvious really what we're doing in a sense. So the plane then, where all these vectors would be found, is what Gauss called the osculating plane. And there are two other planes that will appear next week. If you want to look ahead in the book, they're in section 13.5. You see this osculating plane has for its normal this vector called B, the binormal, which is t cross n, or you could also get it by taking either one of these vectors, V or T, crossed with any one of these. So V cross A, say. The only time that would fail to get the normal to the plane would be if your acceleration were entirely in a straight line, so that the V and the A would be on the same line, then your cross product would be zero. And you couldn't use it to get a normal, but the rest of the time you could. So we're trying to study motion along this curve, and so we will be given the R of t in these problems. If you're not given that, you can't do them, really. Just a second here. So then the R of t being given as a differentiable function, which we're assuming, you can do dr dt, and that's your velocity vector, which is your curve, your line then in purple here. Then the magnitude, which is speed, gives you the SDT. If you integrate that, as we will be in the homework today, you would get a function, scalar function of t, which would be your arc length, your tape measure length along the curve from whatever is your starting point, typically wherever you would be at t equals 0. Then if you take the velocity vector and divide by its magnitude, you get what we call the direction for the velocity vector, which is in blue in my picture. That's the unit tangent vector. And this then, if you wrote it as a differential quotient, dr dt is your velocity over ds dt, your speed, is dr ds. As we said yesterday, that is saying essentially that you're thinking of the r and as how it points changes with arc length, like from one stick to the other. The rate, that rate is what defines your unit tangent vector. Your curvature vector then is the derivative of the unit tangent vector with respect to arc length. It's saying how your line of sight or tangent vector changes with your change in arc length along the curve, so how it changes with your position along the curve. So then if you want to take the dt ds and divide top and bottom by dt, you can write it this way as a differential quotient. And so then you can solve this for the derivative of this unit tangent vector, saying it is the speed, which is a positive number at any point, times the curvature. And we can prove that if you have a constant length vector, like the unit tangent vector, its derivative is going to be at right angles. It may not be a unit vector, but it will be at right angles. I have that proof here. If you were here yesterday, you remember we went through that. So what we have then is a way to get from the tangent vector to a vector that's at right angles to it, that we call the normal. However, it is not necessarily a unit vector. So this thing divided by its magnitude would define this unit vector that is in the orange color that is at right angles to the blue, which is the tangent vector. So that gets us a unit vector in orange pointed inward toward the center of your circle of curvature. A unit vector in blue that points like the headlights would on a little car if you were driving a little car along this curve. And those two are unit vectors at right angles. Their cross product then would also be a unit vector, and that's the binomial. So that's the T and B frame of vector calculus in Maple. And Maple has the command that will let you, the command TNB frame, if you've entered the formula for your R of T that's tracing the curve, and then you can say output equal T or B or N, and it'll produce each of these unit vectors for you. So the magnitude of the curvature vector is the Greek letter kappa and is scalar curvature then, and that's all that there is in the text. The Thomas book as it's written now doesn't really talk about curvature as a vector. As Thomas originally wrote it, it did, but I think it's a mistake not to, so I'm at least mentioning that there is a curvature vector. Okay, so the circle of curvature then is what I'm trying to show here in the dark green in this picture, and when we relate this later this morning to Math 170 and the second derivative sign plus or minus telling you concave up or concave down, I have a circle or a portion of a circle of curvature in these two pictures. So it's a circle which will change from point to point that has the same curvature as the kappa, the magnitude of your curvature vector for the curve traced out by R of T. The Greek letter rho is the radius of this circle of curvature. So it's, if you were building a highway and laying out a curve, each curve would have a radius of curvature then, which would be the radius of a circle that has the same curvature at point to point as your curve has. So it's related to the magnitude of the curvature vector in this way, that one of them is 1 over the other number. So as this number goes towards 0, then this one becomes infinite in a limit, and that would be straight line, 0 curvature, then infinite radius of curvature in a limit sense. So for constant magnitude vector, I'm doing the little proof here that either it's 0 or its derivative is 0, or else the derivative has to be at right angles, because you can take the dot product with itself, and we're assuming constant magnitude, so the dot product with itself is another constant, and then take the derivative of both sides. And if you do your derivative here, product rule, but in the dot product way of multiplying, you have twice the vector times its derivative in the dot product sense equals the derivative of this constant, which is 0. So either the vectors are at right angles or one of them is a 0 vector. So if you have a unit tangent vector, then certainly it's not a unit vector. I mean, it's not a 0 vector, pardon me. said that wrong. Then, if you have something that's definitely not a zero vector, you can tell when you do the derivative by looking at the components whether your derivative would be a zero vector, and assuming it's not, then you know it's at right angles. So we can get this unit normal vector by doing the derivative of the tangent vector, which, as I said, is not necessarily itself a unit vector, but divide by its magnitude, and then that quotient is. So that's how we define the unit normal vector. So that would be the orange vector that's in my picture here. And so the vectors that point like the orange vector are the curvature vector, which might or might not be a unit vector, the normal component of the acceleration vector, the vector that goes into the center of the circle of curvature, and the derivative of the tangent vector, which points this way but might not be length 1. And I drew all of these with different lengths to try and emphasize that in general that would be the case. Of course, they could all be unit vectors. So what we have then finally is that the derivative of this tangent vector is the speed at the point where you are on the curve times the curvature vector, and the curvature vector then is the curvature magnitude times the unit vector that points like it. In other words, the brown and the orange vectors point alike, so one of them is a constant times the other one, and that constant is the magnitude of your curvature vector. So we have these as parallel vectors to each other, which are perpendicular to those two, which are parallel to each other. As I was saying yesterday, if you have a two-component vector, which would be in a plane, you can interchange the order and make one sign change, and what you get would give you a zero dot product. So if you were in the plane and you had a two-component unit tangent vector, you could get your unit normal vector n by this interchange game, and you wouldn't have to do the derivative. But if you have a three-dimensional unit tangent vector, you can't play a game like this. So generally then you would need to do its derivative to get a normal, and then divide by the magnitude to be sure it's a unit normal. So then this is your general formula for how to get from t to n. So then your vector acceleration is capital letter A of t, and that'll be, in general, a vector pointing off toward the center of the circle of curvature, but not directly to it. As you can see, if you look at the rose-colored vector and the vector in dark green that points to the actual center of your circle of curvature. But if you're going along this curve, as the arrows suggest, and it's bending the way that I have shown it, then this acceleration vector and the curvature vector are pointing, your left hand, if you were walking along the curve in increasing arc length, would be pointing in toward the center of curvature if you have what we call positive curvature. This goes with first semester calculus. If you think of Math 160 or Math 170, you take a curve like y equals x squared, which is a parabola, right? And you do your second derivative, it's positive, so you say, as a first semester student, your curve is concave up. That's the same as saying, if you were thinking of walking from left to right, like the arrows, then if you have positive curvature, your left hand is pointing in toward the center of the circle of curvature. If you have concave down, which would be negative second derivative, then it's your right hand that would point in toward the center of the circle of curvature. So you actually have a sense of curvature vector, even in first semester calculus with concave up and down. They just don't say it that way. But this is the same thing, you see. So what I've pictured here really is positive curvature. It's your left hand pointing in toward the center. If your curve were bending off the other way, then that would be negative curvature. It'd be your right hand pointing in. And that's the way the Thomas book originally said it. I've been teaching long enough that, well, I'm not old enough to have done his first edition, but when I was teaching at Oregon State, we were using the third edition, and this is now the 13th edition. But see, Thomas himself has died, and the book publisher keeps the name, but the guys that are writing it, I think, don't really do the curvature as well as Thomas did himself originally. But that's just my opinion. Nobody cares what I think, certainly. Anyway, at least nobody in corporate America cares, right? Like the Wells Fargo Bank, if you see that in the front of the paper today in the Wall Street Journal, they got busted for opening accounts for people that people didn't know they had, and then the account would get overdrawn, and then they were getting overdraw charges. Sure. Anyway, if you want to get the formula for the vector acceleration, write your velocity, it's the derivative, of course, of velocity vector. Write your velocity as the product of the vector ds dt, which is the speed, the magnitude of the velocity vector, and the unit tangent vector that points like the velocity vector. So you have a product rule sort of thing. So then you see you have the derivative of the left-hand factor, which would be then the derivative of ds dt. So that would be a kind of acceleration. So that's going to be the acceleration like the light green component that would come from applying power to your car or putting on the brakes. And then you would have, and so that points like the tangent vector, which I show here in this picture. And then you'd have the speed times the derivative of this tangent vector, which you know points at right angles. That's what we went through over here. And you see that's in turn speed times curvature magnitude kappa, and points like n. So we replace the dt dt with ds dt kappa n. So now you have the speed twice, this factor, and then you get it out of this derivative. So you get speed squared, curvature speed squared. And that would be the magnitude of the green here. Just a second, before you get away, I'll give you a chance to put your name on the sign-up sheet. Then you can go. You pass it back this way. Okay, so then we have curvature speed square as the length of this. So you see that your, as the mechanics here work out, your acceleration is center seeking. It's pointed in this way, but according to Sir Isaac Newton, for every action, meaning like an acceleration, there is an equal and opposite reaction. So the reaction to that is what you feel in the car, because the car will skid, say if it's an icy road, and it'll go out, as you know. So we have the two words. See, if you go back to the Latin, the CENTR is center, and the PETAL is seeking, like a petition. You're seeking something from somebody. And the reaction is center fleeing. The FUG is like fugitive. It's where we get our word fugitive, and that's somebody who is fleeing. Okay? So the actual vector acceleration is center seeking. The reaction, which is what the car does, is that way. And if you skid out, say. And so our vector acceleration then is the vector sum of the two components, where we've resolved it into components along these two unit vectors, t and n, that are at right angles. So they're not necessarily lined up at all with I, j, or k. And the a sub t, then the length of the light green component, would be the second derivative of your arc length formula, and the a sub n, which would be the length of the darker green, is curvature speed squared. And that's what I've said here. Then if you dot this acceleration with itself, having written it in component form, you'd have t dot t, that's a unit vector dotted with itself, so that's just a sub t squared. And then t dot n, they're at right angles, so that's 0. And then n dot n, that's a unit vector with itself, so then you get a n squared. So that's your squared magnitude. That's basically law of Pythagoras with the three vectors there. So then you can solve for a sub n this way. This is also curvature speed squared. That's that. So then your curvature would be this square root over speed squared. You could get curvature that way. You can also get it from going back to here and doing v cross a. So you'd have the a sub t and a n are numbers, so a sub t, v cross t, okay. T and v are parallel, so the cross product is 0. Magnitude, sine of the angle. So v cross a then is the a sub n, v cross n, which are at right angles. So it's really then magnitude v times the a sub n, that's magnitude v cross a. Here n is a unit vector, so its magnitude is 1. So then you can solve and either write it like this, that your normal component is magnitude v cross a over the speed, which is your magnitude v. And then your curvature is that over speed square, so you get v cross a over speed cubed. Okay, so that's over here then. So then if you want to relate this to curvature in a plane, you could come back to where I did some writing here. So thinking of curvature in a horizontal plane, if it's a horizontal plane, the z component is a constant. It doesn't have to be the xy plane, so this isn't necessarily 0, but it would be constant if it's horizontal. So if you use dot for the first derivative or differential quotient and double dot for the second one, you can write in less space. This is in fact the way Newton originally wrote his derivatives, and especially in physics, people still use dot when they mean a time derivative, so like dx dt, and a double dot for second and so on. So the v would look like this, derivative of the constant is 0. The a would look like that with the double dots. So then if you write out v cross a with the ijk and do your basket weave, you see you get 0, 0, and then x dot y double dot, and then coming back you get 0, you get 0, and you get x double dot y dot. Okay, so all you get out of this is if it's a horizontal plane, your v cross a is in the k direction, and so then your ds dt is the magnitude of your first derivative with time. I lost the vertical line there, which would look like that. So having your v cross a like this and your ds dt like that, we can come back to here. So our v cross a is the numerator. I went back from the dots now to the differential quotient because it's easier to see it. And this is your speed cubed. So the V cross A over the speed cubed is that comes out of the determinant here is right here. So then if your curve is y equals f of x, if your parameter is x instead of t, you can set t equal to x in this. So this becomes dx dx, which is 1. This would be second derivative y with respect to x. This would be the derivative with respect to x of dx dx. The derivative of 1 would be 0, and then you'd have times dy dx. So that's 0, so that's gone. So you have the magnitude of your second derivative of y with x over the speed cubed, which if your curve is y equals f of x, it'd be 1 plus dy dx square rooted. That would be your speed cubed. So this is your curvature formula for a curve in the xy plane if the curve is given as y in terms of x. So that's the formula that's on the back side of your long sheet of paper. That's number 12. So this one is number 11, and this down here is number 12 on your sheet of paper. That. So you see the second derivative doesn't exactly give you curvature. It's related to curvature in that you use it in the numerator, but to get the actual curvature, you divide by 1 plus the squared first derivative, then square root that, and then cube. Yeah.
On your handout, it says it's 3 halves.
Yeah, okay. Then you wouldn't have the square root sign.
Okay.
Okay. If you take away the square root sign and just use the brackets, then it would be the 3 halves.
Okay, thank you. I see that.
Okay.
I see that.
Yeah, the handout is 3 halves, but doesn't have the square root sign. And as I was saying, we use the second derivative in first semester calculus for concave up when it's positive or down when it's negative. So that's not quite the same as saying what number the curvature is, but it's certainly related. And this is your actual curvature formula for a curve. So for x squared, you could say you have 2 over 1 plus first derivative squared, square root, and then cube. And then you would get a curvature number, which would be a positive number. And if you did this one, you would get a curvature number, which would be negative. So, okay, well, let's look at some of the homework that goes with the section 13.3. Just a second here. We also need this. And so problem 1 wants arc length. What what is in 13.3 that's different from what we did yesterday mostly is finding arc length. The idea that you can write arc length as a function of t, say, and actually get a number value. So the r of t is given. This would be a helix. You see, your x and y are going around in a circle, but your z is climbing root 5t. So you're going around in a circle, but you're climbing. So it's like a coil spring. And so the r is given. The v is the derivative here, derivative, derivative. V dot v then, you dot this with itself, and you get, as you see, 4 sine squared, 4 cosine squared, and 5. And then you factor the 4, and 4 and 5 make the 9. So you're climbing in this helix path with constant speed. And so the SDT is the square root of v dot v, so that's 3. And so if you're thinking of the parameter between 0 and pi, then arc length would be the integral of ds dt integrated with t. And usually if you're going to use a letter for your variable and you want to write the result as a function, you use some other letter as your upper limit. It isn't really wrong to use t here also, but it's common to change from, say, Roman t to Greek t or something like that, and write it then instead of 3. You see, you're integrating 3 dt, so that's 3t, but you could write it and then change the letter and say 3 tau. And then for a particular value, if tau is pi, you'd be going 0 to pi. So evaluating this between 0 and pi, you'd get 3 pi as your actual tape measure length along this helix as time went from 0 to pi, or the angle through which you're turning down in the XY plane to produce this. So the other thing they want is the unit tangent vector. So you remember that's your velocity vector here over your speed. So it would be this over 3, which would give you minus 2/3, and root 5 over 3. Okay. Then you see this is a 3-component vector. So if you wanted the normal, you couldn't just interchange these 2 components because you have this one. So to get the unit normal vector, they don't ask for it, so we're not doing it. But if you were, you'd do the derivative of this thing, which will be normal and not necessarily a unit vector. So then you do the derivative, and then if it's not a unit vector, divide by its length. That would get the end vector. Okay, problem. So if you look at the maple, I think that's the first one the maple did. So if you bring up vector calculus, you always have to set your coordinates. The problem is, you see, that things could be cylindrical or spherical coordinates, and so you have to say. And then looking at problem 1, you see I've entered the, I've defined the r of t. The colon equal is how you define something in maple, and then colon equal, and then the variable t, arrow, and then your definition, 2 cosine, 2 sine. You see SQRT is square root 5 times t. Okay, so then formula 2 is vector calculus with rather strange symbolism agreeing that that's what the function is. And then they have, as one of the commands in the package, TNB frame, so I can type TNB frame, the vector I've defined. See, I've defined the R of t, and then output with the back quotes equal, and then whichever, the tangent, the normal, or the binormal. So it tells you, number 3, the minus 2/3, 2/3, and root 5 over 3, and that's what I told you over there. And then it also has the command arc length, and you see the 3 pi. Another way you can look at this, if you don't want to do it that way, but use maple, you can do the colon equal and then the vector defined with the angle brackets. And you see when that comes back, the E sub x, E sub y, E sub z are like I, j, k. The reason they don't just do I, j, k is that you might be doing cylindrical or spherical coordinates. Then there'd be the unit vectors for those. Okay, then you do map diff, so that'll get you the vector derivative. So that's the v. Number 6 should match up with my velocity vector. And then you can do TNB frame again and get the same thing. Anyway, the idea is that you can write a formula for arc length, 3t in this case. And so look at problem 7. So it wants arc length for 0 to pi and the unit tangent. So in problem 7, the R is t cosine t, t sine t, 2/3 root 2, t 3/2. So you have product rule. So you have derivative of the left times the right, and then you have the left times the derivative of the right. That's where you get the minus. Derivative of the cosine is minus the sine. Then you have the derivative of the left, the t, so that's 1 times the right. And then you have the left times the derivative of sine, so that's there. And then here you bring the 3/2 down, canceling the 2/3. You have the root 2 and the half power, which I wrote as a radical. So that's my dr dt. That's my velocity vector. Then I dot that with itself. So I'm squaring this out. Cosine square minus 2t sine cosine, and then t square sine square, and then I'm dotting this one out, so that's those 3, and then finally this one would be 2t. And then you see those cancel, the rose color, and then you look at the cosine square from this and the sine square from this one. Put the 2 green together, and that's a 1. Put the 2 blue ones together, and that's a 1 times the t square. And then you have the 2t here on the end. And that is t plus 1, the quantity squared. And so that's your squared speed. And so your speed is the t plus 1. And positive t, that would be positive. Your arc length has to be something that's increasing with the parameter. So then your tangent vector is your dr dt from back here divided by your speed. So that's this. And your s of t itself is the integral of ds dt. So if you're going 0 to pi, you do this integration and go 0 to pi, and you get that for the actual tape measure length as the parameter is increased from 0 to pi. And your arc length function as a function of t would be t plus t squared over 2. So you can write a function typically for these problems that would at any point in time or any value of the parameter tell you the tape measure length from where you started measuring along the curve. So we can look at what vector calculus has done with 7. So you see I've defined the R down there on the bottom of the first page. And it comes back as line 10. And then I do the map diff. And you see that shows the derivative the same way that I have it over there. And then you can do your TNB frame. And you notice you've got these horrible looking denominators, the CSGN stuff. Well, that's because Maple's worrying about absolute value. And the only way that you can get something, notice it will tell you the arc length, number 13. But going back to 7, if you look on the next sheet of paper, the front of your second sheet of paper, where it says we revisit 7. So what I've done then is in between I've said assume that t is greater than or equal to 0. So when it comes back, you see the t has that tilde next to it, which is Maple saying that you've made an assumption that limits the domain. And I dearly wish Maple would not do that because it makes it much harder to read, I think. But anyway, with that assumption then, if you do the TNB frame, it'll give you a reasonable answer. If you just can tune out the wiggle sign all the time, you see then the top is cosine t minus t sine t over 1 plus t, and the vector number 27 then is recognizably this vector that we have here. So if you have something that could be negative and you want an intelligible answer out of Maple, you have to tell it to assume t is greater than or equal to 0. And the price you'll pay then is you'll have to look at this wiggle thing in every place you see a t. But I didn't make the world. So anyway, look at 13. So it wants the arc length for this problem, and the interval is minus log 4 to 0. And notice, however, that your t is increasing. You see, you're going from negative up to 0. And So again, you can do your DRDT with your product rule or with maple. And the thing to do if you're working by hand, when you have a common factor throughout a vector, is to factor it out. And you notice this factor is never negative. So then if you want the speed square, you multiply this by itself, which is your e to the 2t, and then you do your dot product of this vector with itself. And again, you will find these sine cosine products canceling, and you'll have trig identity here to get a green one, trig identity here to get an orange one, and then the one out here on the end to get a purple one. So you have 3 e to the 2t, and then you square root that for ds dt. So then the arc length is the integral of this. If you want to write it as an indefinite integral, you'd have a thing like that. And then if you're doing a definite integral, you're evaluating this between minus log 4 and 0. So you'd have e to the 0 root 3 minus, at your lower limit, e to the minus log 4 root 3. E to the minus log 4 is 1/4, and this minus sign is that one. So you finally get 3/4 root 3 is your tape measure length. And I think that we did 13 with the maple. And you see again, I have the R, the map diff, the arc length, number 16, and I guess that's all that I got maple to do, but the arc length matches anyway. And then the last thing that we did with the maple there is 18. So look at 18 first by hand. So what they're trying to say is that if it's the same curve and the same interval on the curve, you're going to get the same answer for the arc length regardless of how you parameterize it. And it should be, because it is the same geometric figure. So they give 3 ways to parameterize one turn of a helix. Again, remember that's like a coil spring, part of one, a spiral. And so you're going around in a circle with the cosine and sine for the x and the y, and you're climbing with the z over here. So you could use 4t in here and limits 0 to pi over 2. So you notice then that 4 times pi over 2 is the same as 2 pi. Or you could use t over 2 and go 4 pi. And again, if you took t over 2 times 4 pi, that would be 2 pi t, the same as here. Or you could go with a negative here and go minus 2 pi to 0. And you see again, you'd have minus here times minus. So you have a limit that's 2 pi in each case and the limit that's 0 in each case. So each calculation will give you the same length. So let me show you. First one, do your dr dt, then your speed square. Then you see what you have is a factor of 16. So you have 16 from that and another 16. So your the SDT is square root of 32, and your S, then you're going to integrate that, and that would get you the function 4 root t tau as a function of tau. And then if you take your limits on your variable, you get 2 pi root 2. Or with the second one, take this r and do dr dt, and speed square, you'll get 1/2 instead of the 4 root 2. But then when you integrate that, you'll get root 2 over 2 times t, and with these limits, you'll end up with the same answer. And then third time, if you do your derivative, then dot, get sine square, cosine square, and 1, so you get 2. So your speed is root 2, and then integrate, so you get root 2t, and then put these limits on. From minus 2 pi to 0, you have root 2t, from minus 2 pi to 0, so you still get 2 pi root 2. That's their point, that you get the same answer whatever way you parameterize, if it is really the same piece of the same curve. So let's finish by seeing what Maple did. So you see line 19, I've put in I've put in my first version of the R, and done arc length, and it says 20. Then 21, I've put in the second version of R, then arc length, and it says number 22. Third time, and it says number 24. So, see, it says the same thing. If Maple says it, it must be so, right? Well, I think that's as much of your patience as I should try for this week. So either everybody either should have received a test back or should have turned the test in. So anyway, we'll continue next week with sections 13.4 and 13.5.
Is that doing work?